I'm Tobias and I will present our paper, Dynamic 3D Gaussian Fields for Urban Areas. Today, vehicles are constantly capturing visual data of our environment. This enables us to build immersive, up-to-date digital twins of entire cities. However, building photorealistic reconstructions from this data also comes with unique challenges, such as limited viewpoint coverage and varying lighting, weather, season, and even geometry across captures. Given a set of heterogeneous input sequences, captured by a fleet of vehicles at different times and thus in different conditions, our goal is to estimate the function that for a given arbitrary viewpoint at a certain time and sequence outputs the corresponding image, including the dynamic actors present at that time. Over the past years, NeurIPS have been particularly successful in this domain. NeurIPS model a 3D scene with an implicit function parameterized by a neural network and obtain the rendered views from raycasting, sampling the implicit function along the pixel rays. However, raycasting is expensive because for each ray we approximate the continuous rendering integral with discrete sampling, so we need to sample the implicit function many times per ray to do this accurately. Recently, 3D Gaussian splatting proposed a method that uses forward rendering instead of raycasting, meaning that it directly projects the 3D primitives of an explicit volumetric representation to the image plane to form the rendered image instead of casting a ray for each pixel. To enable this rendering paradigm, they choose 3D Gaussians as underlying scene representation, where each 3D Gaussian has a mean that defines the position, a scale and rotation that together form the covariance that define its size and orientation, spherical harmonics coefficients that define the view-dependent color, and opacity to model semi-transparency. This scene representation can then be queried at any 3D point using a simple Gaussian formula. However, while this scene representation is fast to render, it also has several limitations. First, the memory footprint increases linearly with the number of primitives, and large scenes often require millions of 3D Gaussians to be accurately represented, limiting its scalability. Second, the spherical harmonics are restricted to view-dependent effects and cannot model large appearance changes among the input images, requiring homogeneous input data. And third, the 3D primitives have a fixed location, and therefore the algorithm fails drastically in the presence of dynamic actors. To this end, we propose a hybrid scene representation that combines the strengths of 3D Gaussians and neural fields. We remove the spherical harmonics coefficients from the 3D Gaussian attributes, reducing the representation to a geometry scaffold. This also reduces its memory footprint to only about 18% of its original, while still being able to use the efficient forward rendering technique from Gaussian splatting. In particular, we have one set of 3D Gaussians for the static scene in world space and one set of 3D Gaussians per dynamic object in canonical object-centric space. To represent the appearance of the scene, we use fixed-size neural fields that output the view-dependent color based on a position, a direction, and a latent code as conditioning signals. The latent codes are optimized jointly with the representation to accommodate for appearance changes into heterogeneous input sequences. We minimize the query complexity by using hashgraph-based neural fields and limit the query count by skipping irrelevant 3D Gaussians after view projection. This way, we achieve competitive rendering speeds in large-scale scenes at a drastically reduced memory footprint. We represent the varying geometry across input sequences with a correction term that attenuates the opacity of a 3D Gaussian that is not visible in a certain sequence. This allows us, dependent on the latent code, to go from a fully leafed tree in summer to empty branches in winter. For dynamic objects that might have articulated motions, we use the latent codes and a time embedding to deform the 3D Gaussians in local object-centric space before they are transformed to world space. This way, we can model the leg motion, a shopping bag, or the arms of pedestrian as they open the car door. But how do we compose the scene at a global level? Well, if you want to render a view at a certain time and sequence, we should know the latent codes and which dynamic objects are present where. For this, we use a scene graph that stores the latent codes in its nodes, and these nodes are connected through edges that store the coordinate system transformations that correspond to ego vehicle and object poses and the camera calibration. In the scene composition stage, the latent codes and the neural fields determine which static 3D Gaussians should be visible, which local state should the 3D Gaussians of the dynamic objects be in, and which appearance do all of the 3D Gaussians have at that time in sequence. The coordinate system transformations at the edges define the transformation between the static scene to the current viewpoint and the transformation of the dynamic objects to their current location. Finally, we apply the 3D Gaussian rasterizer to obtain the image. To summarize, we use 3D Gaussians to define the overall scene geometry, a scene graph to define the scene configurations, neural fields to define the appearance and the state of the Gaussians, and a dynamic scene composition that puts all of this together into the final rendered view. This architecture enables us to model complex traffic scenarios with a variety of dynamic actors. For example, if you focus on the car in front of us, there's a lady getting out of the car, and we model her articulated motion as she walks away. Apart from modeling a single traffic scenario, we can now also model a range of heterogeneous scenarios with a single representation spanning a large-scale urban geographic area. Thanks so much for watching, and please also check out our project webpage.